In the past, we have learned that there are different ways to represent a point in 2 dimensions. So there's a way we normally represent it. We normally represent a point using what we call rectangular variables. Okay, and we call these rectangular variables, these x and y values, rectangular because if we kind of draw a box from the origin to the point, then x and y are the lengths of the sides of the box. Right? So this is rectangular coordinates. This is the coordinate system we're most comfortable with, that we are most used to. But we've learned about another kind of coordinate system that we can use to describe the same set of points. We could use polar coordinates. The concept of polar coordinates is that if you think about a circle expanding from the origin, and you think about a point lying on a circle centered at the origin, then you can think about this point being associated with that circle with a certain radius and with an angle, a certain angle, measured from the positive x-axis. Okay? And these are polar coordinates. In this section, we're going to take these ideas that we're already familiar with, and we are going to extend them to 3 dimensions. And we're going to have a couple new coordinate systems to allow us to describe behavior in 3 dimensions. It's the cylindrical coordinate system and the spherical coordinate system. Okay. Now, before we jump into that, it will be important for us to remember and review the polar coordinates. So let's go ahead and review the polar coordinate system in 2 dimensions, and then we could take those ideas and extend them into 3 dimensions. Okay. So to do this, we want to find some formulas that allow us to go from the rectangular coordinate system to the polar coordinate system and back again. Okay, and to do this, we could see that just looking at this, trigonometry is probably going to be helpful here, right? We got a nice right triangle when we draw the rectangular coordinate system and the polar coordinate system superimposed on each other. Okay. So what kind of equations do we get? So let's start with the standard trig functions. Okay. Our favorite trig functions are sine and cosine. So cosine of theta is adjacent over hypotenuse, x over r. And what I'm going to do is I'm going to multiply this r to the other side of the equation. That way I could focus on just the x. Okay. So if I do that, then I end up getting x equals r times cosine of theta. And I do the similar thing for sine. Okay, sine of theta is opposite over adjacent, y over r. Multiply the r to the other side of the equation to get the y by itself. Focus on just the y. I get y equals r times sine of theta. So we have 2 equations that allow us, if we have polar variables, r and theta, we can easily find x and y from those polar variables. Okay? Can we go the other way, though? If we know x and y, can we find the corresponding polar variables? Can we focus on r and theta like we have focused on x and y in these 2 equations? Well, for r, what I notice, r is the radius of the triangle, right? The hypotenuse of the triangle, and it's a right triangle. So if I combine that with x and y, I can find r using the Pythagorean theorem. So the Pythagorean theorem gives us r squared equals x squared plus y squared. Okay, and what about theta? How could I relate angle theta here to x and y? Well, again, a little trigonometry. Tangent of theta is going to be opposite over adjacent, y over x. And this is our set of equations that allow us to transition between the rectangular coordinate system and the polar coordinate system. Okay. Notice something interesting about these, and this pattern will carry over to when we go to cylindrical and spherical coordinates also. Notice x and y, we can find them exactly, right? R cosine theta, that is exactly x. R sine theta, that is exactly y. But on this side, we're not finding exactly r or exactly theta. We're finding r squared. We're finding tangent of theta, okay? And that gives us multiple possibilities. There are multiple angles that when I plug them into tangent give me the same value. There are multiple values of r that when squared give me the same r squared, right? If, for example, if r squared is 4, then r could be 2 or -2, right? So there are multiple options here. Why are there multiple options? There are multiple options because the description of a point using polar coordinates is not unique. This is different from how it is in rectangular coordinates, right? This point right here is the point xy. It is only the point xy. There's no other way I could represent this point other than x comma y, right? In the rectangular coordinate system. I can't pick something else for x and something else for y and have it represent the same point. But in the polar coordinate system, it's a little different. In the polar coordinate system, there are different combinations of r and theta that may represent the same point. One easy example, if instead of taking my angle and just going this far, what if I go all the way around the circle and a little bit further? Okay, that's a different angle. But I'm pointing the same direction, and so when I go r units out, I get to the same point. Okay? So here are some alternatives. I could take the same r, and then instead of taking my original theta, I could take that theta and add 2 pi. So I'm going a full rotation around the circle. I end up at the same effective angle, right? I'm still pointing in this direction if I go all the way around and then back again. But it's describing the point differently, okay? And we can also take the radius to be negative. Now, in this case, the way we interpret a negative radius is a radius that goes backwards from where you're pointing, okay? So if I'm pointing this direction, if that's where my theta is pointing, if I have a negative radius, I actually take my point in this direction. Okay? So what I could do, for example, is I could take an angle that goes exactly opposite this angle here. Okay? So exactly opposite. So this is the direction that that angle is pointing, that new angle. This would be, by the way, theta plus an additional half circle, right? Plus pi. So if I'm pointing that way and then take a negative radius, I'd actually move in the opposite direction. I'd move that way. Okay, so a negative value for the radius. The angle's having you look this way, but because the radius is negative, you can imagine going backwards in this direction. Okay? So what that means is another option, if I take that same angle theta and go half the circle around, now I'm pointing in the exact opposite direction as this angle theta, and then if I go backwards, I can get to this same point. Okay? So in the polar coordinate system, the descriptor for a point is not unique. There are actually an infinite number of ways that we could describe a point. So how do we deal with that? So there's a loose rule here that when we have a choice, we usually Generally, we choose R to not be negative. That way you don't have to worry about going backwards. And generally, we restrict theta to a one circular rotation, so between 0 and 2 pi. Okay, so if we're describing a point, we'll often limit ourselves to this coordinate system, okay, to these restrictions. Now, sometimes we have to throw those out the window once we start graphing something in polar coordinates, because really the r and theta could be anything. But if we have a choice, we generally restrict ourselves to these bounds. Okay. So now what we want to do is we want to take this polar coordinate system that we know in 2 dimensions, and we want to extend it so that it works in 3 dimensions. We want to develop these other coordinate systems in 3 dimensions that are an extension of these ideas in polar coordinates. Okay, we'll start with cylindrical coordinates. That's going to be the easier one to think about. It's a very straightforward extension of polar coordinates. And then we'll eventually get to spherical coordinates, which are a little more complicated. Okay, so let's start with cylindrical coordinates. So just as polar coordinates, you could think of them being a coordinate system that's determined by embedding the points in circles. Cylindrical coordinates you could think about as embedding points in 3 dimensions within cylinders. Okay, so let's draw a picture here. X, Y, Z. And I have a point somewhere in space. We have our rectangular coordinates for this point, of course. Okay. And again, we call it rectangular coordinates. Here, let me use this color. Call it rectangular coordinates because if we kind of draw it in all directions, we get a rectangle, or in this case, a box. Rectangular prism. Right? Okay. So what about cylindrical coordinates? Well, what we do is for variables x and y, we just use polar coordinates as usual. Okay. So I draw a circle in the xy plane that goes through just the x and y part of this circle. Okay, so if I extend this to the xy plane, embedded into the xy plane, that's the point I get, right? So the x and y part of this stays exactly the same. Okay, and then just stretch that circle out, so I get a cylinder. Okay, this point then lies on the boundary of the cylinder. Okay, the x and y part of the point right here is just like before. I have a radius, okay, and I'm measuring where I take that radius using an angle theta that's measured from the positive x-axis. Exactly like polar variables, okay? The only difference is now once I get here, I have to go up. I have to go up to this point, and that requires a z variable, okay? And so for cylindrical coordinates, I'm just using polar variables for x and y, and then for z, I just leave it z. So to go from rectangular to cylindrical, we use the formulas we're already familiar with. For polar, x equals r cosine theta. Y equals r sine theta. R squared equals x squared plus y squared. Tangent of theta equals y over x. And to account for the third variable z, we just leave it the same. Z equals z. The z in rectangular coordinates is equal to the z in cylindrical coordinates. Okay? We leave it exactly the same. It just elevates whatever the point is in polar coordinates to the proper plane. Okay? And that's all it is to it. All the same drawbacks and advantages to polar coordinates pretty much also hold for cylindrical coordinates, right? Just as with polar coordinates, the points are not uniquely determined in cylindrical coordinates. And so generally, when we have a choice, not usually when we're plotting a surface, but when we are describing a point, we will choose to describe our point with an r that is positive, or at least non-negative, and we want to restrict our polar angle theta to one full rotation of the circle. Okay, just as before. And then, of course, z could be anything because we want to go anywhere up or down on this cylinder. This point lies on the edge of this cylinder. Okay, lies right on the edge, right there. That's the idea of cylindrical coordinates. I wanted to give you some intuition on how these cylindrical coordinates work, how we plot them. So the big circle in the middle, that's our point. Keep an eye on it. We are going to manipulate our cylindrical variables r, theta, and z. Now z does what we expect it to do. It goes up and down. Okay? R and theta, they act exactly as they do with polar coordinates. So r tells us how far out to go, and theta tells us which direction to point in the xy plane. Okay, so once I pick a direction, r tells me how far I go out in that direction. And then, once I've chosen that point, I can go move up or down by changing the z. Let's take a look at an example. We want to convert this point here, which is given in cylindrical coordinates, to Cartesian coordinates. Cartesian coordinates is another way to talk about rectangular coordinates. Okay. So r, theta, z, how do I know these are cylindrical coordinates? They have the cylindrical variables, right? R and theta, those are the polar variables, r and theta. And then with that, I just tack on the additional variable z. And put those three together, that is the cylindrical variables, okay? So we want to convert this point to coordinate using rectangular coordinate system, right? Before we do that, it's helpful to plot these points. It gives you a little bit of intuition on how these coordinate systems behave, okay? So let's plot this point in 3 dimensions using cylindrical coordinates. So first, I'm going to focus on the first two here. Those are my polar variables, r and theta. Okay. Now, when I plot, I usually focus on theta first. That tells me the direction I'm pointing in. So 4 pi over 3. And I'm going to start by plotting these 2 points in actually just 2 dimensions. Okay. So let me draw them right here. I'll draw the x and y coordinates separately and focus on just my polar variables, 4 and 4 pi over 3. Okay, so I'm going to start by plotting 4 pi over 3, get my angle, okay, 4 pi over 3. So which quadrant is that in? Well, it's bigger than pi over 2. it's bigger than pi. Pi would be 3 pi over 3, right? So 4 pi over 3 is a little bit more. So this is going to be in quadrant 3. Okay, this is the direction that I'm pointing in. So 4 pi over 3, write it over here. Okay, and how far do I go once I point in that direction? Pointing in that direction, we go 4 units out. So since it's positive, we go the direction that we are pointing. If it were negative, I'd go the opposite direction, right? In this case, it's a positive 4. So I'm going to go 1, 2, 3, 4 units out, about there. Okay, 4 units out. Okay, so this would be just in polar coordinates. R theta equals 4, 4 pi over 3. Okay, but of course we don't want just polar coordinates. We want cylindrical coordinates. So let me take what we have here and let me translate what we have so far to our three-dimensional plane, or our three-dimensional space. Okay, so I'm going to start by drawing what we have in the xy plane. So I want the angle to be 4 pi over 3. That's going to be in quadrant 3. I start from the positive x-axis, just like I do here, positive x-axis. And I go around, quarter circle. Try to make this look a little more perspective-y. Quarter circle, half circle would be right about there, right? That's half circle, and I wanted to go a little bit more. So I'm right about here somewhere. Okay, that's the direction I'm pointing in the xy plane. And I go out 4 units in that direction. So 1, 2, 3, 4, something like that. Okay, so that's where I'm at so far. And that's taking into account the polar variables, my angle, and how far I go out once I'm pointing in that direction. Okay. Once I have that angle, then I incorporate my last variable, the z variable. That just tells me how far up I go down. In this case, it's a -3. That means I'm going down. Okay. So now go straight down 1, 2, 3 units. I end up with this point down here. So hopefully you can kind of see where that is. It's behind the x-axis here, or I'm sorry, the y-axis. Okay. In quadrant 3 of the xy plane, it goes down. Okay. Now, I just sketched out where the point was. Technically, the problem doesn't ask for that, but I think it's good practice. Get some intuition on how this coordinate system works. All right. So how do we actually get the points in the Cartesian coordinate system? Well, remember those formulas we have. And I'm going to write them again, but they really should be memorized. We're going to use them throughout the semester. So the formulas that allow us to move from the rectangular coordinate system, or the Cartesian coordinate system, if you prefer, to the cylindrical coordinate system. We have x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, tangent of theta equals y over x, and z equals z. The z in one coordinate system is the same as the z in the other coordinate system. Okay. Now in this particular case, I want rectangular coordinates or Cartesian coordinates. I want x, y, z. right? So if I want to find x, y, z, these are probably the formulas that I want here, right? If I know r and theta, I can find my x. If I know r and theta, I can find my y. And z is just z, okay? So let's plug into these formulas one at a time. So let's do x equals r cosine theta. R is 4, theta is 4 pi over 3, right? So just plug them in. 4 cosine 4 pi over 3. And so we do need to know cosine of 4 pi over 3. I don't have those memorized off the top of my head, generally. If you were good at trigonometry, maybe you did memorize them, but I like to instead focus on the triangles. All of the standard angles that we have, they're either, pointing along the coordinate axes, 0, pi over 2, pi, 3 pi over 2, or you can look at their reference angle and they'll form a 30, 60, 90 triangle or a 45, 45, 90 triangle. In this case, we've already talked about where 4 pi over 3 lives. It lives in quadrant 3. Okay. If this angle is 4 pi over 3, the whole angle here is 4 pi over 3. What I want is my reference angle, which is this angle here. Okay. What would that angle there be? Make it a little bigger so I have room to write. Okay. What would that angle there be? So this is 4 pi over 3. And I like to think about this geometrically, but you need to think about it differently for every quadrant. Okay, the procedure you use in quadrant 3 is different than the procedure you would use in quadrant 4 or quadrant 2. Okay, so in this case, I notice 4 pi over 3 is just my reference angle here that I'm looking for. Okay, plus half a circle, right? Half a circle plus the reference angle I'm looking for is 4 pi over 3. So 4 pi over 3 is equal to alpha plus pi. So if I subtract pi both sides, 4 pi over 3 minus pi, that's my alpha. Pi is 3 pi over 3, getting a common denominator. 4 pi over 3 minus 3 pi over 3 is just pi over 3. Okay, so my reference angle is pi over 3. Pi over 3 is a 60-degree angle. Which means if you know your triangles, the ratios of the sides of this triangle are 1, 2, square root of 3. And generally, the largest sides are opposite the largest angle. Okay, so 1, 2, square root of 3. 2 is the largest side, so it's going to be opposite the 90-degree angle. 90 degrees is always the largest angle. Okay. 1 is the smallest side, so it's opposite the smallest angle. And then 60 degrees, that's our next biggest angle. And so we have that. Okay, so that's how the triangle works. We are in quadrant 3, so both this side and this side are negative. Okay, and once you construct the triangle, you can easily find all the trig functions associated with that triangle. So cosine of 4 pi over 3 is just going to be adjacent over hypotenuse. That's negative 1 over 2. Okay. And by the way, you don't need to do it this way. If you have this memorized, that's faster. Go ahead and use that. Use whatever method you know. But it is useful to be able to calculate the trigonometric functions for these triangles exactly without the use of a calculator. 4 times negative 1/2 is negative 2. So we've got the x down. Okay. We could do something similar for the y. Y, according to our set of formulas, is r sine theta. R, again, is 4. Theta is still 4 pi over 3. Okay. Notice the angle here is the same, so we'd be interested in the same triangle. Okay, so we could use the same triangle and calculate sine. Sine would be opposite over hypotenuse. So that'd be 4 times. Opposite is negative root 3 over 2. Do a little canceling. 4 goes into 2 two times. So negative 2 root 3 is our y. And finally, z equals z. What was our z? We go back up here. Z is negative 3. Okay, so we have the x, we have the y, we have the z. That gives us the same point in the rectangular coordinate system or the Cartesian coordinate system. The point that the cylindrical coordinates are referring to, expressed in Cartesian coordinates, are negative 2, negative 2 root 3, negative 3. Let's take a look at another example. This time we want to go the opposite direction. We have a point in rectangular coordinates, and we want to convert it to cylindrical coordinates. Now, we do have some extra instructions here. We want r to be greater than 0. We want theta to be between 0 and 2 pi. And again, that's because that generally points in cylindrical coordinates are not uniquely expressed, right? There are multiple ways to express them. But if we place these restrictions on the point, then it will be uniquely expressed. Okay, so with those restrictions, the point is unique in cylindrical coordinates. That's why we put those restrictions on them. Okay, so let's start by remembering our formulas. And I'll say it again, you should memorize these formulas. So the formulas for going from rectangular to cylindrical coordinates and back again. X equals r cosine theta. Y equals r sine theta. R squared equals x squared plus y squared. And tangent of theta equals y over x. And the very last one, the boring one that we almost don't need to write down, is z equals z. It's the same z value in both the rectangular and the cylindrical coordinate systems. Okay. So let's jump to it. Let's start by calculating our r. Okay. Now we want to use this formula to calculate r. That's going to be the easiest one because it involves only the rectangular coordinate systems. There are other formulas with r in it, right? This formula has an r in it, this formula has an r in it, but it also involves a theta. Okay, and because we're going from rectangular to cylindrical, we would like to have a way to find r using only the rectangular variables x, y, and z. We'd like to find a way to find theta using only the rectangular variables y and x. You could make these work if you really want to, but you'd have to find at least one of the cylindrical variables first before you can find the others. Okay, this formula anyway is easier to find r, so let's use it. Okay, so here we have r squared equals x squared plus y squared. Just plug in. My x is negative 5, my y is negative 2. So that's going to be 25 plus 4, that's 29. Okay, now remember that's not r, that's r squared. So when we find r, we generally take the square root. And we want to consider all possibilities. So generally we'd use a plus minus, okay? Because both the positive root 29 and negative root 29 square to give me 29. But remember our conditions. To guarantee us uniqueness, to look at give us only one possibility for the cylindrical coordinates, we're going to assume that r is positive. So I don't have to worry about the negative. I'm going to assume that r is positive. So I can take r to be positive square root of 29. And that one's done. Brilliant. Okay. Now let's find theta. Theta is the other tricky one. Theta is the trickiest value to find here. We want tangent of theta to be equal to y over x. Okay. So tangent of theta to be equal to y over x. So in this case, y over x would be negative 2 over negative 5, or if you cancel the negatives, 2/5. Okay? Now that doesn't give me theta, that gives me tangent of theta. So how could I possibly find theta? Well, our initial reaction might be theta would be arctangent of 2/5. Okay? But remember, we got to be real careful with those inverse trig functions, because technically a trig function isn't invertible. In order to make a trig function invertible, we have to restrict the domain. We have to restrict what values of the angle we are going to allow to be plugged in. Okay, it's different for different trig functions. For tangent, we assume that theta is between negative pi over 2 and pi over 2. Okay, so theta equals arctangent of y over x. The angles that it's going to spit out are here. Okay? Theta would be between negative pi over 2 and pi over 2. That's just how we define it. All right? So we have to check, is that the theta we actually want? We could plug it in. This is calculator work, by the way. We could plug it into a calculator, but is it going to give me the theta that I want? What quadrant do I want this theta in? Well, first off, what quadrant is it going to give me? If it's assuming y and x are positive, like I've written here, this is the ratio of y and x, okay? Then this particular arctangent is going to give me something in quadrant 1, right? Going to give me the angle in quadrant 1 where the x, where the y is 2 and the x is 5. It'll give me this theta. Okay, let me draw that down here actually a little bigger. Okay, so since arctangent only spits out angles in this half of the plane, based on what we're plugging in 2 over 5. That is a positive number, so it's going to spit us out an angle here where the opposite is 2 and the adjacent is 5. Okay? That's not the theta we want, though. We are interested in where the y is negative, or the y is negative 2 and the x is negative 5. We want something down here. Okay, so we want this angle. That's the angle we really want. Okay, and let me relabel this. It's kind of confusing talking about that as theta. This will be what arctangent of 2 over 5 gives us. All right, so how do I take the arctangent, which I have to do because I need the calculator to do this, right? How do I take what I get from the calculator from this and then find the theta I actually want? Okay. Well, in this case, it always helps to draw a picture. In this case, we could see that they are exactly a half circle apart, right? So I could take this angle here, add a half circle, add pi, and that will give me theta. Okay, so this isn't really what I really want. What I really want, what's really going to happen here is theta is going to be the arctangent of 2 over 5 plus pi, plus another half circle around. Okay? All right, now this is calculator work. So we could plug that into the calculator. Arctangent of 2 over 5 plus pi. I want to be careful here. Right now I'm in degrees, so arctangent's going to spit us out an angle in degrees. We don't want that. Let's stick with radians. When we're in cylindrical coordinates, when we're in spherical coordinates, use radians. It is the more natural measure. So I'm going to convert to radians, and there we go. That would be the radian measure of the polar angle. Okay, and what is it? 3.522 about. Okay. All right, we've done all the hard part. We found R. R wasn't too bad, but we also found theta. Theta was tricky because if we're using that arctangent, we got to be real careful. Depending on what quadrant our theta is actually in, we may have to adjust the value. Okay? In this case, the theta we actually wanted pointed to in quadrant 3. The arctangent gave us something in quadrant 1, and so we had to add pi to get our actual theta that we wanted. All right, one more value to go, but it's the easiest one. We need z, but z in cylindrical coordinates and z in rectangular coordinates is the same z. So it's, I'll write it up here. It's 5 in rectangular coordinates, which means it'll also be 5 in cylindrical. So our final answer, our cylindrical coordinates, r theta z, is equal to our radius is square root of 29. Our theta, and I could write this as an approximation, but I actually prefer it to be exact. So I'll write arctangent of 2 over 5 plus pi. And our z value stayed exactly the same, it's 5. This example is going to be a little different. We're going to, again, convert from rectangular to cylindrical, but rather than converting a point, we're going to convert the equation of a surface from rectangular variables to cylindrical variables. You'll find that some equations naturally lend themselves to one coordinate system or another. Rectangular variables are great for flat surfaces, like planes. Cylindrical variables, great for, no surprise, cylinders, for example. Okay. So let's take a look at this one. Let's convert it. Now, converting from rectangular to cylindrical, in terms of converting a surface from rectangular to cylindrical, is actually very easy because we can always straight up swap out x, y, and z. Okay? So I can, every time I see an x, I could put r cosine theta. Every time I see a y, I could put r sine theta. Every time I see a z, it's still just z. Okay? But we do have these other equations here, these other relationships, and sometimes it can make things easier. So rather than say x is r squared cosine squared theta, y squared is r squared sine squared theta, I notice right away x squared plus y squared is r squared. Okay? And from this point on in this course, whenever you see x squared plus y squared, there should be a little alarms blaring in your mind. And you should be thinking cylindrical variables, cylindrical variables, cylindrical variables. Okay? Doesn't mean that you will always want to use cylindrical variables in this case, but it means that things might be a heck of a lot easier if you did. A lot of times, when you see an x squared plus y squared, that means, yeah, I should probably be using cylindrical variables here instead. Probably, not always, but probably. Okay, so x squared plus y squared is r squared. And 10y, well, 10y, that really is just y. So that's r sine theta. Okay, and technically we're done. Though we like to tidy up a little bit. When writing surfaces in cylindrical variables, when possible, we like to isolate the r on one side of the equation. Kind of like when dealing with rectangular variables, we like to isolate maybe y on one side of the equation or z on one side of the equation, depending on which variables are there. Okay? So for this one, I notice I've got an r on both sides. So if I divide both sides by an r, I'm left with one r on the left-hand side, and the r on the right-hand side goes away. And so there is the same surface, but expressed in cylindrical coordinates. This example is similar to the previous one, but it's a little more complicated. In this case, we are converting an equation that's in cylindrical form. We want to convert it to rectangular form. Now, that's harder in this case because we have sine of theta, but we don't have an equation that directly relates just r to our rectangular coordinate variables. We don't have an equation that relates just theta or even just sine of theta to our rectangular coordinate variables, right? We have r squared equals x squared plus y squared, right? But we don't have an r squared on this side, it's just r. We have y equals r sine theta, right? But we don't have just sine theta. We don't have an r sine theta here. We have just sine theta. So we have to somehow rework this equation to use these relationships. These are our available moves. These are the only things that we can do. So we need to somehow make this work, okay? And that's a little bit trickier than it was in the previous example where we could just swap out x, y, and z whenever we saw them, okay? So in this case, what are we going to do? Okay. Well, first off, it's important to remember that our final result has to only involve rectangular variables. Sometimes I see students, they say, oh, well, I've got a sine theta, so let's swap out sine theta for y over r. And I mean, okay, but then you have an extra r, right? You're swapping out one one cylindrical variable for another. We need our final result to just have rectangular variables, just x, y, z, okay? So there are different ways to approach this, but I like to look at what I have and try to make it work with what I have. So I have y equals r sine theta, and I'm looking at this one because I already have a sine theta. This is the only equation in my list of relationships here that has a sine theta in it, okay? So looking at that, I say, well, if I could just get an r here, then that would make this work, okay? So how could I get an extra r on this side? Well, one way is just multiplying both sides by r. That means my new equation with that extra r thrown in is r squared equals 2r sine of theta. Now this is looking promising. Now I have r sine theta. And that gives me y. That's what I wanted. That's the goal. But, and I wasn't even looking for this at the time, but I also have benefits on the other side of the equation. Now this is r squared, not just r. And I have an equation that tells me the relationship between r squared and my rectangular variables. So now I can swap out all my cylindrical variables for rectangular variables. R squared becomes x squared plus y squared, and 2r sine theta becomes 2y. I wanted to finish off our discussion with cylindrical variables by looking at some simple surfaces that we could generate with cylindrical variables. Okay, so let's start off by just taking one of our cylindrical variables, r, and setting it equal to a constant. So first off, notice that the other cylindrical variables, theta and z, are not involved in this equation. So that means there are no restrictions on them. Theta could be anything. Z could be anything. Okay. So x, y, z. My radius is 2, so that means as I go out from the z-axis, I want to go out 2 units. Okay, so I want to go out 2 units. Let's say that's 2 units out. But because theta could be anything, I could go around and point in any direction I want. Okay? Go around wherever I want to be. Because that angle theta could be anything. Similarly, z could be anything. There are no restrictions on z. So I could, once I'm on this circle, I could go up or I could go down wherever I want to be. I just have to stay 2 units away from the z-axis. And so I end up getting a cylinder, right? We can express the equation of a cylinder, of course, in in rectangular variables, but this is such a nice form for the equation of a cylinder. It's such a simple equation. Okay, if we wanted to take it to rectangular coordinates, by the way, you'd probably want to square both sides first. R equals 2 is the same thing as r squared equals 4. Which means we get x squared plus y squared equals 4. So it really is a cylinder of radius 2, okay, once we convert it to rectangular variables. But again, much nicer way to express this equation. Very simple, okay? So for the right surface, cylindrical variables are beautiful. Okay, let's take a look at another variable. What if we just set theta equal to a constant value? Say theta equals pi over 6. What do we get in that case? So similar to setting r equal to a constant, setting theta equal to pi over 6, there's no restrictions on r or z, so r could be anything. I could go out from the z-axis as far out as I want, as long as theta equals pi over 6. I could go up and down as far as I want, as long as theta equals pi over 6. So where is theta equals pi over 6? Well, pi over 6 is 30 degrees, so that'll be something like, from the positive x-axis here, that'd be something like this. Okay? Let me draw it a little differently. Okay? So say something like this. Okay? Pi over 6. But because r could be anything, I could go out in this direction as far as I want this way, or as far as I want that way using negative values of r, right? I could go both directions. Because z could be anything, I could go up or down as far as I want. So I will end up getting a plane. A plane that goes through the origin and has this particular angle to it. Okay, that's theta equals pi over 6. Now, I can express this using rectangular variables. Probably want to take tangent of both sides. Tangent of pi over 6 equals, tangent of theta equals tangent of pi over 6. Okay. Tangent of theta, we know that's y over x. So y over x is equal to tangent of pi over 6. Which means y is equal to tangent of pi over 6 times x. So in 2 dimensions, this would be a line going through the origin with slope equal to tangent of pi over 6. Okay. Of course, in 3 dimensions, there's no restriction on the z variable, so it stretches out in that z direction, up and down. Okay. So we get the same thing, but again, it's so nice to express it this way. Very simple way to express this particular kind of surface. For the right kind of surface, cylindrical variables can make things a lot easier. Okay? One more. What if I just set z equal to a constant? Well, in this case, it's exactly like setting z equal to a constant. Using rectangular variables. The z is fixed, but the other variables could be anything. X, Y, z. Z equals 3 is like right here. So as long as I'm at that level, I'm good. I can stretch out as far as I want because the radius could be anything. I could go in whatever direction I want because theta could be anything. So I just end up with an infinite plane that goes through that one point. That's at that level where z is equal to 3. Okay, because I could stretch out from that point as far as I want, and I could do it in any direction because theta can be anything, r could be anything. Okay, so that gives you an idea of some basic surfaces that are easily described using these cylindrical variables. Next, let's talk about the other coordinate system that we wanted to talk about in this section, the spherical coordinate system. Like cylindrical coordinates, spherical coordinates are an extension of the ideas of polar coordinates. Okay, and just like how polar coordinates are based on the geometry of a circle, and cylindrical coordinates are based on the geometry of a cylinder, spherical coordinates are based on the geometry of a sphere. So if I have some point here that is in rectangular coordinates, x, y, and z, the idea is that I find a sphere centered at the origin on which that point lies. Okay, so we have our sphere, and this point lies on the sphere. Okay, so it's right there on the edge of the sphere. So, of course, in rectangular coordinates, we have our x, we have our y, we have our z. We need a set of coordinates to be able to describe a point that naturally lies on a sphere. So for that, we of course want the radius of the sphere. For the radius of a sphere, we use the Greek letter rho. We don't want to use r because we're already using r as the radius of in our cylindrical variables, right? And r is a different radius. It's the radius from the z-axis to the point. Here, our radius here, our spherical radius, is the radius from the origin to the point, which is a little different, okay? And because we're in 3 dimensions, we're going to need two angles to describe this point, okay? So we're going to use the same polar angle that we had before, the theta, but we're also going to use an angle that tells us what angle up or down we're looking, okay? Theta just tells us how far around we go. We need an angle that tells us how far up and down we go. So we measure the angle from the positive z-axis, and we give it the Greek name phi. We name it the Greek letter phi, okay? All right, so now we want to derive a relationship between our rectangular variables x, y, and z and our new spherical variables rho, theta, and phi. Now I'm going to draw a new picture because this one's getting a little busy so we can really see what's going on here. So I'm going to make it a little bigger. I'm going to leave off a few of the lines that we had on the previous one. But the main idea is the same. We have some point that in rectangular variables is x, y, z. Okay, x is how far we go this way, y is how far we go this way, z is how far we go up. So we want a new coordinate system. Maybe I'll make it yellow just to contrast it a little bit more. We need rho. And then this triangle comes down here. We're hitting that XY plane at a right angle. Okay. We need an angle here in the XY plane. That's our theta. It's the same theta we use for cylindrical variables and for polar variables. Okay. And then we need one other angle to describe the angle that this line comes down this way. Okay. And for that, we use the angle phi. So a spherical point can be described using the variables rho, theta, and phi. Okay? All right, let's relate these two. How do we relate rectangular variables to spherical variables? Okay? Well, let's start with the low-hanging fruit. Rho is easy because rho is just the distance from the origin to the point. So I could just use the distance formula, or the three-dimensional Pythagorean theorem, right? Rho squared is equal to x squared plus y squared plus z squared. Okay? Theta is also easy. Theta is also easy because theta is just the same polar angle that we used in our polar coordinate system and our cylindrical coordinate system. And so the same relationship applies. Okay, right angle here. And we could see that tangent of theta is going to be opposite over adjacent, y over x. Okay, exactly like it is for polar and cylindrical coordinates. All right, well, what about the others? So I need to somehow be able to find x, y, and z, and I need to do something with that phi. All right, so I'm going to draw one more line here. I'm just going to take this line here that we already do. I'm going to draw it up here. All right, and let's call that length r. R as in our cylindrical radius, because that's what it is. Okay, that's not actually one of our spherical variables, but we're going to need to find what that value is in order to determine our cylindrical variables, okay, or our spherical variables. So now, using little geometry, we know that if this is phi, this must also be phi, right? Because these are right angles. And we know right angles are 90 degrees. And so this plus this, because it's a triangle, they must be 90 degrees. But also this and this must be 90 degrees, which means this angle and this angle must be the same. Right? Okay. So keep that in mind. Let's see what we could do to find r. Okay? Let's find r in terms of our spherical variables. We, of course, know that just looking at this triangle here, that r squared is equal to x squared plus y squared using the Pythagorean theorem, right? But now let's look at this triangle up here and use some trigonometry to figure out what r is. So looking at angle theta, opposite is r, hypotenuse is rho. So sine of phi, sorry, I think I called this theta, it's phi. Sine of phi equals r over rho. Okay, which means rho sine phi is equal to r. Okay. So now we know this R is rho sine phi. Okay. And now we could use that to figure out x, y, and z. Okay. So specifically, let's do x first. Little trigonometry. Now I'm focusing on this triangle down here. Okay. Cosine of theta is equal to adjacent over hypotenuse. So x over rho sine phi. If I multiply the rho sine phi to the other side, I get x equals rho sine phi cosine theta. And that is one of our important equations up here. X equals rho sine phi cosine theta. That relates x to the spherical variables. If I know the spherical variables, rho, phi, and theta, then I know x. Okay? I can do the same thing for y. So for y, using that theta there, opposite over hypotenuse, so that would be sine of theta. Sine of theta equals y over rho sine phi. If I multiply rho sine phi to the other side of the equation, I get rho sine phi sine theta equals y. So y equals rho sine phi sine theta. Okay? Actually, let me write that just a little lower so it's in line with the other equation there. Y equals rho sine phi sine theta. And now let's get z. Now for z, we want to look at this triangle right here. Okay? Now there's my phi. And so I'm going to relate this side and this side, since those are our two simplest sides. So that means the side adjacent to phi and the hypotenuse. So that's cosine of phi equals adjacent over hypotenuse, which means z equals rho cosine phi. Okay, let me separate these. This is all our kind of our scratch work down here, right? And up here are the actual relationships we are finding. Z equals rho cosine phi. Okay, so we have three equations that relate x, y, and z to our spherical variables rho, phi, and theta. Notice if we know rho, theta, and phi, then we could exactly find x, y, and z. All right. Over here, we have an equation that helps us find rho, an equation that helps us find theta. We need one more that helps us find phi. All right. So for that, we're actually going to use this same formula here. And we just are going to solve for this in terms of phi because we have a relationship between rho and xyz up here. Okay. So I'm going to take this and I'm going to isolate the phi. And then if we assume that rho is positive, which is a little bit of an assumption, we know that we can generally take the radius to be positive or negative. So if we take our spherical radius, if we assume it's positive, then we can write this as the square root of x squared plus y squared plus z squared. Okay. And then the phi we usually choose will be between 0 and pi. Let me explain that. Okay. Angle theta here, we want it to go all the way around. Okay. So just as before, we usually limit theta. We usually limit theta. Let me write the limits up here. We usually require rho to be greater than or equal 0 and theta to be only one rotation of the circle. Okay, but what about phi? Well, phi we don't want it to be less than 0, just as before. If phi equals 0, we're pointing straight up. Okay, phi equals 0 is positive z-axis. But if we then allow phi to increase, we go down until we get to here. After that, we start going back around. And rather than allowing ourselves to go back around, that actually gives, what happens is we end up with two different ways to describe a point if we allow phi to go too far. Because I could get to, say, this point over here. I could get there by either letting phi go all the way past pi, or I could let phi go down here, this angle, and then let theta go around to here. Does that make sense? So because of this, we don't generally let phi go past pi. Now again, there are exceptions. Okay, oftentimes when we deal with certain kinds of equations in spherical coordinates, we implicitly allow theta, phi, and rho to go past these bounds. But if we want to have every point in three-dimensional space have a unique spherical coordinate, then these are the limits that we impose on rho, on theta, and on phi. Specifically, that means if phi is between 0 and pi, that means we can safely take the arc cosine function here, because we know the output of the arc cosine function is between 0 and pi. And so that gives us a relationship between our rectangular variables x, y, and z and our spherical variable phi. So phi is arc cosine of z over x squared plus y squared plus z squared, all under a square root. That relationship, these relationships are relationships between our rectangular variables and our spherical variables, and we should memorize them. Okay, these are important. We will be using these for the rest of this class. I wanted to give you some intuition on how these spherical variables work, how we can plot points with them. Okay, so the big circle here, that represents the point. We're going to manipulate our spherical variables and see what happens to that point. So let's start with phi. So if we manipulate phi, it changes the angle which we come down from the z-axis, how the angle we're going up or down. Okay. Theta is our polar variable, and so it changes exactly as we're used to. It extends from the positive x-axis and it goes around. Okay, and then rho, our rho, that's the radius, that's how far out we go once we have our direction from our angles. Larger rho, we go out further, smaller rho, we go in. So you can see how by manipulating theta and phi, we can hit every point on a sphere for a fixed radius, rho. Now let's take a look at an example. For this first example in spherical coordinates, we want to convert a point that's in spherical coordinates to an equivalent point in Cartesian coordinates or in rectangular coordinates. Now, before we jump into the math of doing that, let's plot the point. Where is this point at? Let's get some practice plotting the point. Okay. I like to start with my angles first because that tells me what direction I'm pointing. Then the radius, tells me how far out I go in that direction. Okay. So I'm going to start with our polar angle theta. So this is going to tell me the angle I make with the positive x-axis, the angle I make going around the z-axis like this. Okay. So for this one, it's 3 pi over 4. 3 pi over 4 is 2 pi over 4, which is 90 degrees. 2 pi over 4 is pi over 2, plus another pi over 4. So it's making an angle kind of like this. Okay, so 3 pi over 4. Once I'm pointing in that direction, now let's worry about that azimuthal angle phi. So for phi, I'm going to, it's the angle I come down from the positive z-axis. Okay, so in this case, it's pi over 3, that's 60 degrees. Okay, so 60 degrees, and I'm pointing in this direction in the xy plane. So I'm gonna come down in this plane. Okay, so that's pi over 6, 30 degrees, 45, pi over 3, 60 degrees, somewhere like there. Okay, in this plane where my polar angle is telling me to go. So that's phi equals pi over 3. And now let's put it together. So I've taken my angle, I've gone all the way around here. My polar angle. I've taken this guy and I've come down here in that plane. And so now this is the direction I'm moving in. Okay, in this plane. This direction. And I want to go out 1 unit in that direction because my radius is 1. Okay? And so that's the point. It's going to be right here. There's the point in spherical variables. Okay? Now, of course, that's not what the problem asks. So let's now do what the problem asks. Let's actually convert the point from spherical to Cartesian. So let's remember our formulas. And again, these are formulas that you should memorize for this course. X equals rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine phi. Rho squared equals x squared plus y squared plus z squared. Tangent of theta is y over x. And phi is arc cosine of z over square root of x squared plus y squared plus z squared. Okay. So with that done, with these formulas ready, we can easily find x, y, and z. We want x, y, and z, we just plug into these 3 formulas right here. Okay, finding x, y, and z, z, z. Okay, so x is going to be rho sine phi cosine theta. Here, let me break them up like this. X equals rho sine phi cosine theta. Rho was 1. phi is pi over 3, and theta is 3 pi over 4. So sine of pi over 3, cosine of 3 pi over 4. Okay? So we're going to need to find sine of pi over 3. We're going to need to find cosine of 3 pi over 4. Now, perhaps you have those memorized. If so, fantastic. I was taught, the way I was taught, I did not memorize them. Instead, I break them into triangles. Okay? So let's sketch out where they are. This will help us with those other two calculations also. Let's start with sine of pi over 3. Pi over 3 is in the first quadrant. It's 60 degrees. Pi over 3. It's a 30, 60, 90 triangle. The other angle here is 30 degrees, or pi over 6. Because it's a 30, 60, 90 triangle, I know the ratios of the sides. The ratios of the sides are going to be 1, 2, square root of 3. And I remember which side goes where, because bigger sides are always opposite bigger angles. So my biggest side, the biggest number is 2. The biggest angle is 90 degrees, so they're opposites. Okay? The smallest side is 30 degrees, and so it's opposite the smallest side, which is 1. Okay? And so that's pi over 3. I'm also going to need cosine of 3 pi over 4. 3 pi over 4 is in quadrant 2, right? 3 pi over 4 goes all the way over here, like this. Okay? What I really need here is my reference angle. My reference angle is going to be pi over 4. I know that because if I put together the angle that I have here, 3 pi over 4, plus the angle that I want my reference angle, just geometrically, I could see that's going to be a full circle pi, right? So I could think, what do I need to add here plus 3 pi over 4 that would give me a full half circle? That would give me pi. And indeed, pi over 4 plus 3 pi over 4 is equal to pi. Okay? Now, pi over 4 is 45 degrees, so we're dealing with a 45, 45, 90 triangle. The ratios of the sides for a 45, 45, 90 triangle are 1, 1, square root of 2. But I also have to take into account what quadrant I'm in. I'm in quadrant 2, which means the x is negative in this quadrant, the y is positive. Okay? Once you have the triangles built, the trig functions are easy. Sine of pi over 3, that'd be this first triangle right here. Sine of pi over 3, that's opposite over hypotenuse, that's root 3 over 2. And then cosine of 3 pi over 4. 3 pi over 4 is this triangle right here. Cosine is adjacent over hypotenuse, negative 1 over root 2. And so the x, I find very quickly, is multiplied all together, negative root 3 over 2 root 2. Okay? Or if you'd like to rationalize the denominator, multiply top and bottom by root 2, I get negative root 6 over 4. Okay? Either one of these would be acceptable. Okay? Let me actually put those down there. There we go. Okay, we've got our x done. Same thing with y. Y is rho sine phi sine theta. So y is rho sine phi sine theta. And it sounds like a lot of work because we got to do all that again, right? The angles stay the same, so we can use the same triangles. Phi is still pi over 3. Theta is still 3 pi over 4. So I've already have the triangle for pi over 3 right here. Sine of pi over 3 is root 3 over 2. Sine of 3 pi over 4, let's look at this triangle right here. 3 pi over, sine is opposite over hypotenuse. That's 1 over root 2. And so I get positive root 3 over 2 root 2, which is fine as an answer, but if you choose to rationalize your denominator, you get root 6 over 4. Okay, so we have our x, we have our y. One more, let's do our z. So looking at our formulas, z is rho cosine phi. So let's plug that in. Rho is 1, and phi, just as we plugged in here and here, it's still pi over 3. And so we're still going to be using that same triangle. Okay, this triangle right here, pi over 3. Cosine of pi over 3 is going to be adjacent over hypotenuse. That's 1 over 2. One times a half is just a half. We have our x, we have our y, we have our z. We put them together. We have the same point, but written in rectangular coordinates. The x is negative root 6 over 4. The y is positive root 6 over 4. And the z is 1/2. Let's take a look at another example. Here we want to go the other way. We have a point in rectangular coordinates. We want to express it in spherical coordinates. And we want to do it in such a way that rho is positive, theta is between 0 and 2 pi, and phi is between 0 and pi. So the usual ranges we want for those values. Okay? So this tends to be just a little trickier because you notice these equations here, which give us rho, theta, and phi in terms of rectangular coordinates x, y, and z. Notice on this side, it's not just rho by itself. It's not just theta by itself. We do get phi by itself, but that's kind of the exception, right? These other two we'll have to think about carefully to make sure we get the correct values, especially the theta, all right? Let's start with the rho, though. So we know rho squared is equal to x squared plus y squared plus z squared. From the problem, we know x is negative 2, y is 2, and z is 4. So plug those in. Negative 2 squared plus 2 squared plus 4 squared. I get 4 plus 4 plus 16 is 24. Okay, now that's rho squared. I want rho. Because I'm only interested in the values of rho that are positive, I could take the positive root of this. I don't have to worry about the plus and minus that would normally come when you take a square root. Okay? And I could tidy that up a little bit. I could pull a 4 out of that, right? 24 is 4 times 6, and the square root of 4 is 2. So I could rewrite this as 2 square roots of 6 if I want to make it nice and tidy. Okay? So, hey, rho's done. One down. Let's handle our trickiest one next. Tangent of theta is equal to y over x. So next, tangent of theta equals y over x. In this case, that means tangent of theta is equal to, let's look up our y and x. X is negative 2, y is positive 2. X is negative 2, y is positive 2. So that's tangent of theta is equal to negative 1. Which means we need the arctangent of negative 1, right? Now you want to be careful here. Remember, these arctrig functions are tricky because they only output angles in certain ranges. Arctangent is only going to output angles between negative pi over 2 and pi over 2. Okay? But we want an angle where x is negative 2 and y is positive 2. So we want x is negative 2, y is positive 2. So the angle we want is not in the output range of tangent. So this isn't going to work for us just as is. We're going to need to adjust. Where is arctangent of -1 going to spit us out? So arctangent of -1, tangent is y over x. So in order for tangent of theta to be negative, the y and the x have to have opposite signs, right? They have opposite signs in quadrant 2, but also in quadrant 4. Okay? So arctangent is going to spit out this angle right here. Okay? Because, whoops, hold on. The y is -2, the x is +2. So x and y are still opposite signs, but that is where the arctangent is going to spit out the angle. So we need to correct for it. So theta is not just arctangent of -1, it's arctangent of -1 plus, how do we get here? Whoops. How do we get from here? From here? We need to go a half circle around, right? They're half circle apart. So we are going to add pi. All right? Now, this arctangent -1, you might know it off the top of your head. If not, you could pull out your calculator. Arctangent of -1 plus pi. Now you want to be careful here. We're in degree mode right now. We want to be in radian mode. Okay. By the way, in degree mode, it's a little easier to see what the true output is. It's -45 degrees. Okay. Makes sense if you look at the triangle, right? The legs of the triangle have the same magnitude. And so that indicates that we have a 45-degree angle here. And it's just below the x-axis, which is why it's negative, right? But whenever we're dealing with spherical coordinates or cylindrical coordinates, we want to be in radians, not degrees. Radian is the more natural measure mathematically. So I'm going to add pi, like the formula says, and then I'm going to make sure I'm in radians. And I get 2.35619,449. Okay, so you could either write that, or you could note that arctangent of -1 was 45 degrees, -45 degrees, so it's -pi/4, right? So either use the decimal form, or you could just plug in -pi/4, right? And so that gives me exactly, instead of having to round with decimals, I get exactly 3pi/4. Okay, all right. That's the hardest one. I've got the rho, I've got the hard one, theta. Let's do phi. Phi's not too bad because I can calculate it exactly so long as I'm using a positive radius here. Okay, and I am. So final calculation, phi is equal to the arc cosine of z over square root of x squared plus y squared plus z squared. And rather than plugging in every x, y, z, I know that square root of x squared plus y squared plus z squared is just rho. I've already found that. So might as well plug that in instead of calculating this again. Let's plug in. Z is, what was it? It was 4. And rho is 2 square roots of 6. So 4 over 2 square roots of 6. Or, if I cancel out the 2's, arc cosine of 2 over root 6. Okay? And that will be exactly, that is definitely a calculator problem. We don't know the triangle with an adjacent of 2 and a hypotenuse of root 6 right off the top of our heads, right? So let's plug this into a calculator. Pulling it over. One arc cosine of 2 over square root of 6 Again, be careful here. We want our answer in radians, not degrees. Okay? If ever you're not certain, if it's unclear from the problem whether you should be doing radians or degrees, the answer is radians. If the problem specifically is using degrees, use degrees. But if otherwise, use radians. Radians should be considered the default value. It is the more natural measure. Mathematically, it is a more convenient and useful measure. Okay? Degrees is, we have a better intuition for it perhaps, but mathematically there's no reason why 360 degrees is just the magical number for the number of degrees of a circle. That goes back to the Babylonians, who like to have a base 60 numbering system. Also why we have 60 minutes in an hour, 60 seconds in a minute. Okay? All right, we have everything we need. Rho, theta, phi. Let's put it all together. Our final answer. This point expressed in spherical coordinates is the rho is 2 square roots of 6. The theta, we were able to calculate it exactly. In this particular example, we get 3 pi over 4. Generally, you may need a calculator for it, right? To find the arctangent, just be careful that you don't just automatically take that arctangent. Sometimes we may need to adjust. Okay, not always, but sometimes. You have to be aware of when to do it. All right, draw it out. And then our phi, I'll just round to a few decimal points here, 0.615. There is our final answer. Do another example. In this one, we are given an equation in rectangular coordinates. We want to convert the equation to an equation in spherical coordinates, right? Now, converting from a rectangular equation to a spherical equation is, from rectangular to spherical is pretty straightforward because we can always just swap out x, y, z with these values, right? And that technically would do it. But if we could have a little bit more finesse, we want to do it. In this case, I notice I have x squared plus y squared plus z squared here. And just like for cylindrical coordinates and x squared plus y squared, here, if you see x squared plus y squared plus z squared, you should immediately think spherical coordinates, spherical coordinates, spherical coordinates, okay? Because it means that spherical coordinates might make this problem a lot easier. Doesn't mean for sure it will. Doesn't mean it will always be the right answer, but a lot of the times. If you have x squared plus y squared plus z squared, spherical coordinates are often a good approach. All right. So I'm going to swap this out for rho squared. I could swap out z squared for rho cosine phi squared. So z squared becomes rho cosine phi. And because the z is squared, so is this. X squared plus y squared plus z squared is rho squared using this. And notice co-squared times, or co-squared of 3 pi over 4. That's a constant, right? 3 pi over 4 is not angle theta or phi because those need to be variables. 3 pi over 4 is just a constant. I'm just plugging it into cosine. Okay. Now, I could simplify this. You could find what cosine of 3 pi over 4 is and evaluate. But in this case, I think you'll find it a little bit easier if you don't. All right? Because once I square the left-hand side, notice I have rho squared on both sides. So let's divide both sides by rho squared. That gets rid of rho squared on both sides. And I get cosine squared of phi equals cosine squared of 3 pi over 4. Okay. So what does that mean? Well, because of our limitations on phi, if we limit phi to being between 0 and pi, then there's only one value of phi that can make these two cosines equal to each other. And that's if phi is 3 pi over 4. That's the obvious thing to plug in, right? Obviously, if phi is 3 pi over 4, these two, the left-hand side of the equation equals to the right-hand side of the equation. And in this case, that's the only possibility. And we're done. Look how nice this resulting equation looks. Naturally, in spherical coordinates, this equation just has a very nice form in spherical coordinates. Whereas back here in rectangular coordinates, man, that is unpleasant looking, isn't it? That is hard to work with. So there are just some problems that are much easier to deal with in spherical coordinates. Let's do another example. This one's a bit tricky. We want to find an equation in rectangular coordinates that is equivalent to this equation in spherical coordinates. Rho equals 3 cosecant phi. Now, converting from a spherical equation to a rectangular equation is a little bit trickier because we don't have something that tells us exactly what rho is. We have rho squared, right? And while we have something that tells us exactly what phi is, do we really want to plug this into this? Not my favorite, right? Let's see what we could do here. Now, the very first thing I notice is that I have a cosecant phi. I don't have any cosecants of phi in any of these equations. So I'm going to rewrite this so that it doesn't involve cosecant. I know cosecant of phi happens to be 1 over sine of phi, right? Now I'm dealing with sine, and I have sines a few places, so maybe I can make this work, okay? This is looking more promising. But I don't want it in the denominator, so let's multiply both sides by sine of phi to get it out of the denominator. Remember, the name of the game here is you need to match what you have with these equations here. Somehow, you need to manipulate what you have here to match your available options here. Okay, so that's what I'm trying to do. I'm trying to get into some form that's going to work, maybe with one of these where I have a sine phi in it. Okay, so if I multiply both sides by sine phi, I get rho sine phi on the left-hand side of this equation and just 3 on the right-hand side. Okay, that's looking a little better, isn't it? But it's still not quite there. I don't have just rho sine phi anywhere in these equations. I have x equals rho sine phi cosine theta. I have y equals rho sine phi sine theta. But I don't have just rho sine phi. So how can I, what else can I do here? Okay, can I multiply both sides by cosine theta? Well, let's try it. So rho sine phi so I'm going to multiply both sides of the equation by cosine theta. Now that is great for the left-hand side of this equation because rho sine phi cosine theta is x. And so I get x equals 3 cosine theta. But that's as much as I could do, right? The right-hand side, I can't do anything with because I don't have just a cosine of theta anywhere. Can't deal with it, okay? And which means this equation is not done in its present form because I need all my variables to just be rectangular variables. I can't have any spare rhos or thetas or phis flying around this equation. Okay, so this is a great idea, but unfortunately it just didn't work. Okay, and you'll find that the same thing happens if we multiply both sides by sine of theta. The left-hand side, you'd be able to turn into a y, but on the right-hand side, you'd have a sine of theta just floating around that you can't do anything with, right? Okay. So now what? Well, if you think back, here I've got a x equals rho sine phi cosine theta. Here I've got a y equals rho sine phi sine theta. Is there any way I could combine those so I could just focus on rho sine theta? Specifically, what happens, is there any way to put a cosine and a sine together to get them to go away? What we're going to do is we're going to use one of the Pythagorean identities. Okay? Recall that cosine squared theta plus sine squared theta equals 1. One of the most important trigonometric identities. Okay, what does that mean in this case? If I take x squared plus y squared, okay, and I'm squaring them so that I could get cosine squared and sine squared, I'd get this squared plus this squared. So rho squared sine squared phi cosine squared theta, that's what x squared becomes, plus y squared becomes rho squared sine squared phi sine squared theta. If I pull out the rho squared sine squared phi, I'm left with cosine squared theta plus sine squared theta, which is just 1. So I just get rho squared sine squared phi. And so I get something that's involving just rho and sine of phi. And that's looking very promising over here. Okay, what this amounts to is a bonus equation in our list of equations up here that is sometimes very useful. In the right situation, this bonus equation is very useful. X squared plus y squared, no z squared, is equal to rho squared sine squared phi. Okay. With that bonus equation, I can now take this. If I square both sides, I could get a rho squared sine squared phi, couldn't I? So I'll square the left-hand side. That gives me rho squared sine squared phi. If I square the right side, 3 squared is 9. And now rho squared sine squared phi I know is x squared plus y squared. And now I've gotten rid of all my spherical variables. I have just rectangular variables, and I'm good to go. Okay. All right, this one was a little trickier, wasn't it? We got a bonus equation out of it, so that's useful, I guess. But this one was a little bit hard. Why was it hard? Well, it helps to realize what kind of surface we're dealing with here. In 2 dimensions, x squared plus y squared is a circle of radius 3. If we add the 3rd dimension, there's no restriction on x, so it just stretches out in the z direction. I get a cylinder of radius 3. But we described that cylinder in spherical coordinates. What do you think would be a more natural coordinate system for describing a cylinder? How about cylindrical coordinates? Right? So we can describe a cylinder using spherical coordinates. But as you can see, the math can get a little bit gnarly. When you're dealing with cylinders, it's best to use cylindrical coordinates. When you're dealing with spheres, probably best to use spherical coordinates. Choosing the right coordinate system for the right situation can greatly simplify the mathematics. Okay, so if instead of writing this formula in cylindrical coordinates, if, at the very beginning, if we had this formula in cylindrical coordinates instead of spherical coordinates, this would have been a much, much easier problem. To finish off this section, I wanted to talk about some simple surfaces that we can describe using spherical variables. So what if we just take our spherical radius rho and set it equal to a constant? Say 3. What do we get? Okay. Well, theta and phi could be anything. So we could be pointing in any direction. The only thing that changes is how far out we go in that direction. Okay. So I could be pointing, this direction, I got 3 units, okay? Or I could be pointing this direction, I got 3 units. No matter which direction I go, I can point in any direction. With theta and phi, it allows me to point in any direction in 3 dimensions. But I have to go out 3 units. Okay? So if I could point in any direction, but I'm always restricted to being 3 units away from the origin, that means I have a sphere. Right? I've got a sphere. I can go in any direction, but all the points, no matter which direction I'm going in, are 3 units out from the origin. Okay? Makes sense if we're dealing with spherical coordinates, that one of the basic shapes that we get is a sphere. Right? What if we set another variable equal to a constant? Okay? Maybe theta equals pi over 4. Okay? So theta equals pi over 4. That is right here and then goes out 45 degrees, something like that. Okay, so that's how far out I'm going to go. But then my phi, my azimuthal angle, could be anything. So I can go in any direction, up or down, as long as I'm pointing this way. Okay, and then my rho could be anything, so I could go out as far as I want. Okay, and generally when thinking about surfaces, those restrictions we have on rho, theta, and phi, where rho could only be positive and phi has to be between 0 and pi, generally we don't think about those when dealing with surfaces. So rho could be negative. My radius could be negative, which means I could go out any distance in this direction, in any direction, okay, as long as I'm staying pointing this way. And then I could go either backwards or forwards. Because I could choose rho to be negative or positive. And so I end up getting this plane. Just like I did with cylindrical coordinates. So when I set theta equal to a constant, I get the plane pointed in that direction. Okay? What about setting phi equal to a constant value? Okay, let's take phi equals pi over 4. Okay, so for phi, you start by pointing straight up and then your angle goes out from there. So pi over 4 would be like right here, right? Anywhere around that z-axis you want to go. Okay, so pi over 4. But theta could be anything. So as I said, that pi over 4, I could go around the z-axis, okay, because that theta lets me rotate around. And my rho could be anything, so I could go out any amount once I'm pointing that way. So because I could go around, and because I can go out, I end up getting a cone. Okay, I just have to stay at that angle of pi over 4. But what's more, my rho, my radius, could be positive or it could be negative. So I could go out in this direction, or if I'm negative, I could go out in that direction. So I end up getting a double cone. So when b is equal to a constant value, the surface we get in spherical coordinates is a double cone.